Okay, we had some confusion with this simply because, well, because we were having trouble getting the sign of the voltage drop across the inductor correct. And one of the problems was that we had I3 in this direction, this loop was going in this direction, so it was confusing, and it confused me too, and trying to explain why the sign of the voltage across the inductor was what it was, okay? So we decided that it would be much easier if we had the current going in the same direction as the loop whenever possible, okay? So we can choose either direction for our current, so it's perfectly all right to do this. And then in this loop, I2 is, if we're doing I2, it's in the direction of this loop, and our I2 is also positive in the direction of this loop, right? It's not always possible to have all the currents positive in the most convenient direction of the loop. But you can, if you got, like 3 things to choose 2 of them to be positive, okay? So you have fewer negatives to worry about and change the sign. And particularly because the most confusing thing is the direction of your inductance, your voltage across the inductor. Try to have the current through your inductor in the same direction as the loop, okay? Again, not always positive to do that. If it isn't, well, you need to think it through, okay? So, anyhow, for this loop, of course, you've got I2 in the direction of the loop, so you have a voltage drop I2R1 through resistor R1, right? And you're going to have a Q over C for your capacitor. By writing this, we're assuming then that if Q is positive, you have a drop from here to here, right? So if Q turns out to be positive, it's got to be positive on the plate that you first encounter while you're going around the loop. Okay? If the loop happened to be in this direction and the current was in this direction, then you'd actually end up with a negative Q over C for that loop. Okay. And then we have a voltage drop going in this direction, because as we go in this direction through here, we go from negative to positive, which is not a drop, it's a rise, so it's a negative drop. Okay? Now eventually we'll put that Vs on the other side of the equal sign. If we just think in terms of voltage drops, this is what we get. Okay? For the second loop, I3 is in the direction of the loop as it goes through R2, so you have a drop I3R2. We'll go ahead and bite the bullet and do the inductor. Okay? If I3 is increasing, and I3 is in this direction, that means that your inductor will be exerting, or will produce an EMF in the opposite direction, which means that this will be positive, this will be negative, right? Because it's going to be pushing the current in this direction. So that your voltage drop as you go across in this direction, well, you're going from positive to negative, right? So your voltage drop is positive. Now, using voltage drops instead of voltage changes and then having the directions of the loops and the directions of the currents, it's a little complicated, so you got to be sure you understand what's going to happen if this current is increasing, right? And if you had a case where the loop was going in this direction and the current was increasing, you'd need to reason that out. You need to figure out if the current's in, well, you need to figure out which direction the inductor is going to push in. Then you'll know if it's pushing in this direction, this is positive and this is negative, right? And if it's pushing your current in this direction, then this is positive and this is negative. And then the direction of your loop tells you whether that's a positive or negative L dI/dt. Okay? So that's a little, it's one of those simple things where you have all these binary relationships, either positive or negative, and then put them together and hold it together in your brain. And it's very simple logic, which just shows you how bad human beings are at it, because it confuses all of us. except for the weird ones that really can understand that logic through several steps. But nobody can understand it through more than 5 or 6 steps. I don't think. Okay. Anyhow, then you have your I2 through the R1, which is a positive drop, and through the capacitor, which is also positive, right? So right there are our equations, but of course, we've got our I1, I2, and I3 everywhere, except we got di3 dt, right? Okay? And we can't really do anything about that like we could over here, because your di dt here was just your second derivative of the charge on the capacitor. But here, your capacitor is branching off before it gets here. So it's not just your dq dt of the capacitor that's driving the current through the inductor, okay? It's a combination of that and the influence of this as they work through these nodes. Does that make sense? So you end up with a perfectly good differential equation in I3. Everything else can be done in terms of the charge on the capacitor. Well, okay, what's the other thing? I2 is dq dt, right? Because there's no branching from here to here, okay? So you replace I2 with dq dt, and you got this here, right? And now you get into a system of differential equations that we probably aren't going to solve, because there's actually an easier way to look at this, okay? But you see what the source of it is, okay? This equation is easy to solve, assuming that your Vs is like a sine or a cosine or a power of t, okay? So that's our situation.